So you see everything, right?
Yeah, everything is good.
Excellent.
All right. So welcome everyone to the third APPROX session today. It's the third and final APPROX session today, APPROX Session 6. We have 4 talks, and the first talk is going to be given by Vadim Grinberg on approximating star cover problems. Each speaker has, there's a 10-minute slot for each speaker. Feel free to unmute yourself to ask a question or type a question in the chat. And with that, I'll ask Vadim to get started.
Yeah, thank you. So, my name is Vadim, and I'm going to present you our joint work with Vadim Agamlas from EPFL, approximating star cover problems. So, first, we need some definitions. So we're considering a finite metric space F union C, where F is a facility set and C is a client set, as we call them, and D is a distance function, which is a metric. So a star is basically a tuple of I and Ci, where I is a facility and Ci is a set of clients. A star cover is a collection of disjoint stars that basically cover all set of clients. So set C is partitioned into different stars associated with corresponding star centers, which are facilities. And the load of star is just the total sum of distances between a star center, the facility, and the clients that belong to this star. And the load of a star cover is the maximum of loads of the stars that are included in the cover. So that's how we call these numeric values in our work. So if every other definition is clear, okay. So we are considering star cover problems. So we like to introduce you to the topic. A very well-known K facility allocation problem can be interpreted and defined as follows: given number K, we need to find a star cover of size at most K. So there are at most K stars, K facilities opened, minimizing the total load of all stars. So sum over all stars in the star cover, load of each star. We are studying different problems in our work. So we call them minimum load K star cover and minimum size star cover problems. The first problem is the following. We are given a number K, and we need to find star cover of size at most K, minimizing its load. So minimizing maximum load of stars that are included in the cover. Minimum size star cover is basically a reflection. We are given a load bound T, which is a real number, and we need to find a cover of load at most T, minimizing its size. So we just swap the bounded minimization. Surprisingly, these problems are one of the most poorly studied in the field of star cover or facility allocation problems. So the most notable results, which are among the few known, are that they are both NP-hard, even if we allow clients to be facilities, so we allow opening facility and allocation of any clients. And in this case, there are several constant factor bipartite approximations by Ivan et al. And by Ahmadian et al. And for the special case where metric is line metric, it has been shown by Ahmadian in 2016, I believe, that it is still NP-hard, but they provided a p-TAS, which is quite a non-trivial algorithm. But it's for general case where sets of facilities and clients are not the same. And we are focusing on the most general setting where sets of facilities and clients are arbitrary, not necessarily the same, and where metric D is also arbitrary metric. We are not using any assumptions. So our results are the following. So basically, for any epsilon, for any constant epsilon, in the minimum load K star cover problem, we are able in polynomial time to find a star cover of size most 1 plus O of epsilon K and load at most O of 1 over epsilon squared times out. So bicriterial approximation. And we obtain a similar bicriterial approximation for minimum size star cover problem. So given epsilon and an instance of minimum size star cover problem, we can find the star cover of load at most 2 plus O of epsilon times t times the bound, and size at most big O of 1 epsilon squared times O. So the algorithm are based on roughly the same ideas, and the second one and the first one, they differ technically a lot, but the tools that we use are the same. So we'll focus on, I'll try to give you a brief overview of the first result, if I have time, of course. So our approach is based on linear programming rounding. So let's consider like a standard linear programming linear programming formulation of minimum size, minimum load k star cover problem. So basically, this is a polytope which points are star covers of load at most t and size at most k. So I think the constraints are quite clear. So the first one ensures that we have load at most t, second one that size at most k, and the other constraints are just like standard constraints that assure that every client belongs to exactly one star, and that we do not assign clients to stars that are not present. We don't assign clients to facilities that are not open. Yeah. And let's, by L of Ix, we define the fractional load of facility I with respect to solution X, assignment X. So by alpha beta approximation, about alpha beta approximate solution, we mean the solution, the fractional solution, such that the constraints on the load and on the size are not satisfied perfectly. That is satisfied approximately with the corresponding, respectively, the approximations are alpha and beta. But all other constraints are satisfied. And our algorithm for is on a very high level is quite simple. So first, using binary search, we find t star the approximation on the optimum with optimal load, and then we put this number t star and k into the linear program that was defined before. We get a feasible solution, and then we just round it up to get an alpha beta approximation where alpha is big O of 1 over epsilon squared and beta is 1 plus O of epsilon. Yeah, and for minimum size star cover problem, the algorithms are roughly the same. So how exactly does the algorithm work? So I think I'll try to give a brief ideas. So what our main point is. So basically, when we are given a solution to the linear program, we want to open some facilities, close the others, and redistribute the demand between open and closed facilities. We do this by rerouting, which is basically adding the demand of one client facility to another client facility. Standard procedure. And we can estimate the change of load that a facility gets after we reroute something. So the main question is, how do we bound all these terms when we try to reroute? And that is the main point of our algorithm, but I think I don't have time to explain how exactly it works, because it's extremely non-trivial and quite complicated. So yeah, maybe I shall stop right here in my presentation.
All right, let's thank Vadim. We have, sorry, Jarek, you have a question?
I have a question. Do you have lower bounds on approximability? You just mentioned NP hardness.
Yes.
But...
So we have lower bounds on basically we have lower bounds on approximability using this approach. So if we try to use this linear program as it is, like standard linear program, then we show that any integral star cover, size at most 1 plus epsilon k, has load at least omega of 1 over epsilon. So we cannot get load approximation better than O of 1 over epsilon. Our approximation is O of 1 over epsilon squared, so it is not tight. And for size, And for minimum size Tarkov problem, we have like a similar round. We show that we cannot get a load approximation better than 2, like for multiple reasons, not only because like, this linear program is bad. And yeah, so that's it. I want to mention that we did not show any general inapproximability results. Yeah.
I have a quick question. So have you thought of a configuration style LP where for each facility, I mean, you have configurations which are all the...
So exponential size one, right?
Yeah.
So we have thought about it, but we did not come up with any good algorithms that use it. I know that in paper of Ahmadian, she showed a similar to our lower bound in approximability. So she showed that if we use exponential configuration style LP, so we cannot get better.
All right, let's thank Vadim again and move on to the next talk in the session, which is going to be given by Sharat Ibrahimpur. Sharat, can you share your screen? Okay, so the next talk is by Sharat Ibrahimpur, and he's going to be talking about a 4/3 approximation algorithm for the minimum 2-edge connected multi-subgraph problem in the half-integral case.
Hello, everyone. Thanks for coming to this talk. Today, I'll be presenting our result on a 4/3 approximation algorithm for the 2-edge connected subgraph problem in the half-integral case. This is joint work with Sylvia Boyd from U Ottawa, Joseph Cherian, Robert Cummings, Logan Kraut, and Lou Wong from U Waterloo, and Zoltan Sigeti from Grenoble. Let me start with the problem formulation. In the 2-edge connected multi-subgraph problem, we are given an undirected graph G bar on n vertices, and we are given non-negative costs on the edges. Our goal is to find a 2-edge connected spanning multi-subgraph of minimum cost. Here, spanning means that we want to span all vertices, and multi-subgraph means that we are allowed to use more than one copy of an edge. To compute the cost of a subgraph, we need to account for the multiplicities of edges used. This is a very standard operation. There's a very standard operation called as metric completion, using which we can basically assume that G bar is complete and that C is a metric, i.e. Triangle inequality satisfied by the cost. Here's a quick toy example that I've shown just to clarify like what kind of solutions we are looking for. This problem is NP hard, so our aim is to obtain approximation algorithms for this. And another quick remark is that there's a very well-known problem called as the traveling salesman problem that can be seen as 2ECM plus the Eulerian property, i.e. we want like the subgraph to be such that 2-edge connected subgraph to be such that every vertex has even degree in it. We can write a linear programming relaxation for 2ECM. Here, the variable xc denotes the number of copies of edge E that we want to use. The LP is very natural. The objective function just models the cost. These constraints say that we want to use at least 2 edges along any cut. This is what ensures 2-edge connectivity. I also added like these constraints, which say that the fractional degree at each vertex should be exactly 2. This can be added without increasing the LP value, and this is due to something called as the parsimonious property. And as you can see, if you write this LP out, this looks the same as the well-known subtour elimination LP for TSP. That's why like I've written that like both these LPs are identical. That's the close connection between 2ECM and TSP. The fractional versions are the same. Here's a celebrated result known as like the Christofides algorithm, which gives a 3/2 approximation for TSP, and it also implies a 3/2 bound on 2ECM. Wolsey gave a polyhedral analysis of this result, so this is what I've written here. In the title, I mentioned that we consider half-integral instances. So these are instances of 2ECM where the LP is optimized by a solution that is half integral. What this means is that if you were to multiply x by a factor 2, then all the coordinates are integral. The reason we consider such instances is because these can be seen as the simplest non-trivial fractional solutions. And there's another reason, like there's a well-known conjecture due to Schallekamp, Williamson, and Van Zylen, where they claim that the integrality gap for TSP, if you consider the subtour polytope, then it is attained on half integral instances. That is one of the reasons why such instances have gained popularity. More than 2 decades ago, Carr and Ravi showed that the integrality gap of 2 ECM polytope is at most 4/3. And they do this by showing that the vector 4/3 x dominates a convex combination of incidence vectors of 2 ECM solutions. The result is constructive, but it is not polytime. Our contribution is that we give a polytime algorithm for this. That's our theorem 1. Given a half integral instance and an optimal half integral solution x to this instance, in quadratic time, we can compute a 2H connected spanning multi-subgraph whose cost is at most 4/3 C transpose X. By using the well-known meta-rounding algorithm of Carr and Bempala, we can in fact efficiently compute a polynomial-sized convex combination of 2H connected subgraphs such that the convex combination is dominated by 4/3 X. Let me first start with a very simple reduction. That is very standard thing to do for this problem. So given a half integral solution X, we consider the multigraph G, which is induced by 2 times X. The idea is very simple, like given a half integral solution, for every half edge, we include 1 copy of that edge. And for every 1 edge, we include 2 parallel copies of that edge. And we use the same cost on these edges. This gives us a 4 regular 4H connected graph, G. And here's the reduction. So finding a 2 ECM solution in G bar of cost at most 4/3 C transpose X this reduces to finding a 2H connected solution in G of cost at most 2/3 the cost of G. Here cost of G is sum of all the edge costs in G. Here we lose a factor 2 because you can see that the cost of G behaves like 2 times C transpose.
I think we are experiencing some technical. Sharat, you seem to be back, but you're muted. Okay, Sharat, we lost you for a bit there, so can you just go back to?
Sure. Yes. So where was I? Was I in the reduction?
Yes.
Okay, sorry. Yeah, so the reduction is that finding a 2H connected solution in our given instance of 2 ECM is the same as finding a 2H connected subgraph in this 4H connected 4 regular graph of cost at most 2/3 the cost of G. And here we lose a factor 2 because the cost of G is like 2 times C transpose X. Our high level strategy is as follows. We mimic Carr and Ravi's proof strategy with some simplifications. We get rid of their gluing step and we handle all remaining cases by using an extension of Lavoisier's splitting off theorem. And this is due to Bang-Jensen et al. Our proof naturally leads to a polytime algorithm via the method of conditional expectation. This is another main theorem in our work. Given a 4 regular 4H connected graph and an arbitrary excluded edge E in this graph, and let's just say we also have like cosh, arbitrary edge cosh, I'm allowing cost to be negative as well. Then in quadratic time, we can find a 2H connected subgraph whose cost is at most 2/3 the cost of G minus E. And the subgraph avoids the edge E. Just to give you the intuition, I'll proceed with an example, our proof strategy. Let's say we have a graph, regular 4-edge connected graph on 10 vertices, and this UV is the edge that we want to exclude. So we want to use an inductive or a recursive strategy. We are gonna go to a smaller instance of the problem, and what we do is there is this operation called as splitting off, which allows us to get rid of the vertex B while still obtaining like smaller instances of the problem, like smaller valid instances. So one way of performing this operation is to shortcut the edge UV and VX by forgetting the vertex B. And the remaining two edges, we also shortcut again at V. So this gives us the instance G1 here on 9 vertices. We can do another such operation where we shortcut UV and VY and ZV and VX. This gives us another instance of the problem. And the extension of Loasch's splitting off theorem that I was mentioning says that for every edge UV in such a graph, there are at least 2 such choices of performing a splitting off operation. And so basically we'll always get 2 such instances. And once we do this, we inductively solve these 2 sub-instances. For now, I'm just talking about a constructive result. So inductively, we can obtain a convex combination for these uniform vectors in each of these instances. Then we can lift these solutions back to the original graph. I'm not going to describe the lifting operation, but it's not very hard. And lifting the solution, what happens is that these convex combinations are a bit like biased. On the left-hand side, the convex combination that we get has more weight on the edge VY and less weight on the edge VX. And on the right-hand side, this thing is symmetrically opposite. So a simple averaging procedure on these 2 sub-instances gives us the required convex combination for the vector 2/3 times the incidence vector of the entire set. Our polytime algorithm just follows by recursing on the cheaper of these 2 branches. So as you can see, because this left subinstance pays more for the edge VY, we should recurse on the left side if VY is the cheaper of the edges, and we should recurse on the right if VX is the cheaper of the edges. And this can lead to negative edge cost in the instance. Like I've not defined the lifting operation, nor like how I create a valid subinstance on the smaller graph. But there is a way of defining cost, and this can lead to negative edge cost. But this is okay for our theorem because we allow negative edge cost. I'll conclude my talk with this. So we gave a 4/3 approximation algorithm for 2 ECM on half integral instances. And the open question that I would like to mention is that what's the exact value of this integrality gap for 2 ECM on half integral instances? We know of examples where it's at least 6/5, and Karen Ravi's proof showed that it's at most 4/3, and also our result. What's the true value? With this, I would like to end my talk.
Right. Thanks, Sharat. I think we are a bit running a bit late, so let's save questions for later, and we'll move on to the next talk, which is going to be given by Xiangyu Guo.
Yes.
Xiangyu, can you
Let
just
me share the screen. And okay, can everyone see the slides?
We can, but do you want to like make your slides full screen or something? We start slideshow.
I already make it full screen. That's strange. What about now?
Yeah, this is good.
Okay, great.
All right, so our next talk is by Xiangyu Guo, who's going to be talking about on approximating degree-bounded network design problems. Go ahead, Xiangyu.
Okay, this is a short summary of our work on approximating degree-bounded network design problems. And this is the joint work with Guy Corsarts from Rutgers and Bonded McCartney from Shanghai University of Finance and Economics, and Daniel Wells from Munich, and my colleagues Shili and Jia Yixian from Buffalo. And in this paper, we studied two problems. The first one is degree-bounded directed standard tree. The input is a directed graph G with some non-negative edge cost and a degree bound. And in addition, we have a root R and some K terminals, which are just a subset of vertices. The goal of the problem is to find the minimum cost tree rooted at R such that it connects R to every terminal while respecting the degree bound. That means each vertex in the tree should have outer degree less than the degree bound. So the highlighted edges forms an example of the feasible solution. And there are a lot of related works on degree-bounded network design problem in undirected graph. And this undirected case is well studied, and people have obtained almost optimal by criteria approximation. Here, the first number in this tuple is the approximation ratio on the cost, and the second number is the violation of the degree bound. And both of these results are obtained via iterative rounding, and the ratios on both factors are almost optimal. However, in the directed case, the problem is significantly harder. So even without the degree bound, we cannot approximate directed standard tree within any constant ratio, assume P does not equal NP. And the best, actually, we cannot approximate within some polylog factors, but I think the hardness assumption here is not NP, P does not equal NP. I don't remember the actual assumption. And for polynomial time algorithm, the best approximation ratio we have is a polynomial factor. Here, K is the, remember, K is the number of terminals, but usually you can think K is of the same order as N. So this is essentially a N to the epsilon approximation ratio. However, if we allow quasi-polynomial running time, then there is a tight approximation ratio, log square K over log K, assuming the projection game conjecture. And this is just obtained very recently. But for the degree-bounded DST problem we studied, there is essentially no non-trivial approximation algorithms. So we only know a lower bound implied by the DST hardness. Note here, you cannot approximate the degree bound within a log n factor. So you have to violate it at least by this factor. This is by a simple reduction from the set cover problem. Our main result for this problem is a quasi-polynomial time running time algorithm with this bi-criteria approximation ratio. And this is the first non-trivial approximation for the problem. And our approximation ratio is very close to the lower bound. And the algorithm is based on a novel LP formulation. And in particular, the technique can be easily generalized to handle other constraints other than the degree bound constraint. Our second result is on the degree bounded group standard tree on trees problem. Here, the input graph is itself a tree rooted at some vertex R. And again, we have edge cost and degree bound. But now the terminals are partitioned into K groups. And the goal is, again, found a tree T. But now it only needs to connect R with every terminal group, which means you only need to connect one vertex for each group, like in this example for these highlighted edges. So why do we study this problem? Because first, the hard instance for the DST problem is essentially a GST on trees instance. And our algorithm for the DBDST problem essentially converts the input to a GST on trees instance. And for this problem, we give a polynomial time algorithm with almost a tight approximation ratio on both the cost and the degree violation. And this improves upon the previous results of Kosas and Newton by shaving a log n factor from the degree violation. Now let me give an extremely high-level sketch of the algorithm for DBDST problem. So consider the optimal solution, T star, and you can decompose it into many small trees. Actually, you can recursively apply this procedure to partition the tree into many small like edges or 3-node subtrees. And then we can encode this partition procedure using an object we call state tree. And since this is a balanced partition, this state tree will be a full binary tree with very small depths, order log n depths, since this T star has only order n many vertices. And our idea is to enumerate all such state trees, since it's of shallow depth, and it has a very nice structure. And our key idea is to show that this tree is a subtree of a large tree called a T-circle. We call it a T-circle. And this T-circle can be constructed in quasi-polynomial time. And then we just encode this tree using an LP, which is of the same size of the tree T-circle. And after we solve for the fractional solution, we can use some standard rounding procedure to get a state tree for the original optimal solution. And you may note that where is the degree bound? So in the algorithm, the degree bound seems to be absent, and it's actually embedded in the tree T-circle. And when we construct this large tree T-circle, we will enumerate all the degree bound. And this is why I said at the beginning that our algorithm can be generalized to handle ask constraint, since any constraint that can be enumerated in poly n time in some per vertex manner can be encoded in such a tree. And that's all. Thank you.
All right, let's thank Xiangyu. Maybe you have time for a quick question.
Mm-hmm.
Okay, there are no questions, then we'll move on to the final talk in the session, which is going to be given by Neng Wang.
Okay, let me share my slides. Can you see the slides?
Yeah. So Neng is going to be talking on the paper on the approximability of presidential type predicates. Go ahead, Neng.
Thanks for the introduction. So this is a joint work with Aaron Potenchin. Let me first define what presidential type predicates are. A presidential type predicate is a Boolean predicate of the form sign of a times x1 plus x2 plus ... plus xk. Here, xi's are Boolean variables, and we use -1, 1 to encode a Boolean variable. And we assume that a is a positive integer, and this linear sum is never 0 for every input x. So we can think of this predicate as a vote, where every variable either votes 1 or -1, and vote of x1, which we call the president, has a special weight a, and the votes of the remaining variables x2 to xk, which we call citizens, have the same weight 1. And we remark that this is a special case of balanced linear threshold functions, where every variable can have a different weight. Balanced meaning there is no constant term, so if we pick x uniformly at random, it's equally likely to have px equals 1 or px equals -1. So a few examples. So when a equals k minus 2, this is known as the monarchy function. So in this function, the monarch x1 gets their way unless all the citizens unite against the monarch. So when all the citizens unite, they will have a weight of k minus 1, which is just enough to beat x1. And when a equals 1, this is the well-known majority function. Next, let me define constraint satisfaction problem. I believe probably all have seen this. An instance of CSP is specified by a set of variables which take values in some finite domain D. In our case, D is the Boolean domain, and a set of constraints where each constraint is a predicate applied to a subset of variables. And the goal is to find an assignment that satisfies as many constraints as possible. So a canonical example is the 3 satisfiability problem, where we have a set of Boolean variables, and a constraint is simply the OR of 3 variables or negated variables. For example, we can have the constraint x1 or x3 or not x4, or the constraint not x3 or x5 or x6. And we have the same goal, find an assignment to the variables that satisfies as many constraints as possible. So we know there's a trivial algorithm for 3SAT, which is to assign the variables uniformly at random. And under this algorithm, every constraint is satisfied with probability 7/8. So this algorithm, simple as it is, satisfies a 7/8 fraction of constraints in expectation. So the next question is, can we do better than 7/8? And the answer is no. In fact, Hastad showed that even if the given instance is perfectly satisfiable, it is still NP hard to do better than 7/8. So this leads to the notion of approximability and approximation resistance. So we say that a Boolean predicate P is approximable if given a nearly satisfiable CSP instance whose constraints are all of form P, there is a polynomial time algorithm that finds an assignment that's better than a random assignment. Otherwise, we say P is approximation resistant. So this is a key definition in this talk. Let me emphasize that what we want to do is find an assignment that's better than a random assignment on a nearly satisfiable instance. So there's a rich body of work in this area. On the algorithmic side, we know the max cut is approximable. So random assignment satisfies max cut with probability 1/2, but the algorithm by Gomez and Williamson has an approximation ratio of 0.878. We also know that majority function and monarchy functions are approximable. They are both special cases of presidential type predicates. On the hardness side, Hastad showed that 3SAT and 3XOR are approximation resistant, and Potetchin showed that there's a balanced linear threshold function that's approximation resistant, assuming the unique games conjecture. And there have also been several useful criteria for approximation resistance. So our result is the following. We showed that for the presidential type predicate, if the weight of the president is at least a constant times k, where k is the number of variables, then the predicate is approximable for sufficiently large k. So our result filled in a huge gap between what was previously known about presidential type predicates. So previously, for large A, we know that monarchy predicate, which is the case where A equals k minus 2, is approximable. And the almost monarchy predicate, where A equals k minus 4, is approximable. For smaller A's, Hast showed that predicates close to majority are approximable. And his result implies that for presidential type predicates, if A is big O of square root of k, then the predicate is approximable. And our result, again, says that when A is a constant times k, the presidential type predicate is approximable. Okay, so how do we design approximation algorithms to show that presidential type predicates are approximable? So our algorithm has 2 steps. So the first step involves, there's a canonical semi-definite programming relaxation by Prasad-Raghvendra, which is essentially optimal under unique games conjecture. And the first step of the algorithm is to solve this SDP on the given CSP instance. And the SDP will produce a set of biases and pairwise biases. And what we need to do is to come up with rounding schemes that take these biases and pairwise biases as input and output an integral solution to the original CSP instance. So we need to understand what kind of biases and pairwise biases were given. So let's look at a single clause. We will obtain biases B1 to BK and pairwise biases B1 to B13 to BK minus 1K. And the intuition is that these biases and pairwise biases, they actually come from some distribution of satisfying assignments. So Bi is actually the expected value of Xi in this distribution, and Bij is the expected value of Xi times Xj in this distribution. So a consequence of this, which is also a key fact in our analysis, is that this weighted sum A times B1 plus B2 plus plus Bk is actually expected value of A times X1 plus X2 plus plus Xk for some satisfying assignments X. And we know this is at least 1. And we will design our running scheme such that it outputs an assignment whose expected value is approximately the multiple of this weighted sum of biases. So we call that presidential type predicates are balanced. So its expected value is 0 under a random assignment. So if we can have a positive expected value, that's better than the random assignment, which implies that this predicate is approximable. So our final running scheme looks like this. And I'd like to stress that we actually use the pairwise biases. So the previous algorithms for monarchy predicate and for the majority function, they only use biases. And we actually have some evidence that using pairwise biases is necessary to approximate presidential type predicates in general. So let me conclude with a few open problems. So we showed that these predicates are approximable, but actually our techniques only work for a sufficiently large k. So what about smaller k? And we showed that we can do a tinier bound better than random, but what is the best we can do? And finally, can we analyze more general balanced LTFs? So we know there's a balanced LTF that's approximation resistant under unique games conjecture. So can we give a decidable characterization for which balanced LTFs are approximable and which balanced LTFs are approximation resistant? And that's all I have. Thank you for your attention.
All right, let's thank Neng. Are there any questions? Jarek?
So I have a question. So you mentioned that you have these pairwise biases, but is it like a general way that you can construct the distribution by giving these pairwise biases, or is there a natural limit to this?
So this pairwise biases, they actually come from this solving this SDP. So it's not something we construct, but something we obtain from this SDP.
Okay, so I guess you deduce from that there exists such a distribution because they come from the SDP, right?
Yes.
Okay, so let's thank all the speakers in the session. This was the last APPROX session for today. There's a random session in 20 minutes. So that's it.
Thank you. I'll keep this session running. So if someone would want to continue discussing it, it should be running still. Thank you.
See you.
I might have a question for Xiangyu, if he's still around.
Hi.
Hey, if you don't feel like answering it, let me know. But there was a previous version of the paper on archive. Is there a So what is the difference between that one and the latest one, or is it the same?
I'm not sure which version you are referring to, because we. Oh, okay, I know. That one deals with the lens-bounded directed standard tree, and also a buy and bulk problem. Also, both in the directed standard tree setting. But that paper, how should I say it, coincides with another paper independently done by others, and they publish it. So on some other conferences.
That's the one by, so you're referring to Guge Nagarajan, right?
Right.
Right. So the new version focuses more on the degree constraints.
Yeah.
Is that the
So we
idea?
did the degree bounded setting.
I see. Yeah, I read the older version and it was a very nice paper, and I thought this is something new, but then I got confused because the title is different. But yeah, I see. So yeah, it makes sense to focus on the degree bounded one. Yeah, thank you.
Okay, no problem.